Unit Operation Classroom. We are now discussing GATE 2023 question 15. Which one of the following statements is related to octane number is not correct? Before we look into these options here, let's first find out what is knocking and how is that related to octane number. In spark ignition engine, we know that the fuel and the air mixture is injected into this chamber here, and the piston moves, and correspondingly, the air fuel mixture gets pressurized, and of course, the temperature. According to the PVT relationship increases, and at right around near the spark plug, the proper timing just gives a spark, and of course, a flame is produced, and that propagates and keeps the piston pushing down, and correspondingly pressure decreases, and that converts into rotating motion. So this cycle is continuously repeated. Now, what is knocking? In knocking, it's a spontaneous, uncontrolled mini explosions inside the engines. What happens? Let's say there is some kind of a hot spot is produced inside this chamber right here, where there we have air and the fuel mixture. Air and the fuel mixture. Because of the hot spots, it may self-ignite, and correspondingly, a spurious pressure wave is created that interferes with the main pressure wave, and that creates knocking. And of course, the knocking is not desirable. So octane number reflects resistance to knocking. So higher the octane number, the better or the smooth running of the engine is. So we really look for higher octane number of the fuel. Okay. So let's see how the structure of the fuels are related to the octane numbers. Straight chain alkanes, called linear alkanes, have low octane numbers. Let's say, look at this is my straight chain. So this is N-heptane. There are seven carbon atoms right there. So this is octane number zero. So this zero octane number. Whereas a branched hydrocarbons, as there is a branching of the hydrocarbons, then that results in higher octane numbers. So if we have isooctane, which is basically 224 trimethyl pentane, 1, 2, 3, 4, 5 pentane, and 224 trimethyl pentane, which is isooctane, that is an octane number of 100. So as you can see, the branching gives favors higher octane number. Aromatic hydrocarbons also have high octane number. Let's look at the benzene has an octane number around 101. Toluene has an octane number around 120. So as you can see, the straight chain hydrocarbons have low octane numbers, whereas if there's a branch chain, so there is more branching in the hydrocarbon, it results in more octane, higher octane number. Similarly, the aromaticity of the hydrocarbons gives a higher octane number. So these are desirable in my fuel. Okay. So let's look at the first option. It says linear alkanes with higher carbon number have higher octane number. That is not true. So linear alkane, let's say this is the normal pentane has an octane number 62. As the carbon number keeps on increasing, this is normal hexane. This is around 25. See how octane number is reduced. And C7, which is heptane, normal heptane has an octane number 0. So high for linear alkanes, higher the octane number or the carbon number, these have lower octane numbers. So this option is false. A option is false. Okay. So this A option is false. Let's look at option B. Branching in linear alkanes increases their octane number, which you have just now seen that as the hydrocarbons become branched, so there is more of this derivative, ethyl derivatives, etc. Branching of the hydrocarbons that results in higher octane number. So this option B is true. Okay. Catalytic reforming of hydrocarbons increases the octane number. So let's look at what is catalytic reforming. In a catalytic reforming operation, this converts low octane paraffins or the naphthenes into higher octane aromatics and isoparaffins. So basically, this is the cyclic hydrocarbons, and this is the aromatics, and isoparabens, of course, is the branching. Let's quickly see. In the catalytic reforming, there's a various reactions happen. One of them is, of course, dehydrogenation. Naphthalene, which is the like the cyclic hydrocarbons, there are no aromatic bonds here. There is no aromatic bonds that dissolves into benzene. So if you have like a cyclohexane, which is just like this, and that is converted to a benzene, which we just normally just write this one as like this. Okay. And of course, there's the dehydrogenation, hydrogen comes out. If you have methyl cyclohexane like this, which of course is something like this, here is a methyl group, and in presence of platinum catalyst, approximately 500 degrees Celsius, this is converted to toluene. So catalytically reforming, what it does, it takes cyclic hydrocarbons and converts them to aromatics. So that's very desirable. That increases the octane number. Similarly, dehydroisomerization. So let's say you have a straight chain hydrocarbon. When you do the catalytic reforming, it produces the branched hydrocarbon. So again, that increases the octane number. So that's very desirable. Similarly, dehydrocyclization. So you have, let's say, you have a straight chain hydrocarbon, normal heptane, and then that cyclizes. So basically, then what happens? It forms a cyclic compound. So if you have like normal hexane, so that is cyclized to no, not this one, converts to cyclohexane. Okay, and then there is aromatization of the compound of this compound, and that produces the aromatic bonds. Okay, so what it basically the dehydrocyclization, so it produces the aromatic compounds. Okay, so as you can see, the basic purpose of catalytic reforming is so useful that it converts low octane paraffins and naphthens into high octane. Also, it boosts the octane number of the fuel if you do the catalytic reforming. So this option C, which says catalytic reforming of hydrocarbons increases the octane number, so that is also true. Okay. And gasoline quality is measured in terms of number. We know that is also true. So basically, only option A is wrong, but option B is true. Okay. Option C is true. Option D is true.